Having examined how maneuvering an aircraft can apply loads to the structure, we will now consider the loads that can be applied by gusts and turbulence. For simplicity, we will consider what are called vertical, sharp-edged gusts. An upgust will suddenly increase the angle of attack, without time for the aircraft as a whole to respond. The vector diagram shows that the change in angle of attack is a product of the true airspeed and the speed of the vertical gust. The increase in angle of attack will increase lift on the wing, the result of which will be to bend the wing upwards. Keeping in mind that structural weight must be kept to a minimum, the designers must ensure the strength is adequate for expected gust intensity. To ensure adequate strength, 3 design gust values are used, which can be plotted on a gust load diagram. The origin of the gust load diagram is 1g. Positive CLmax is plotted, and there is a new design speed to consider, VB, the design gust speed. At VB, the structure must be strong enough to withstand a 66 feet per second sharp-edged vertical gust, both upwards and downwards. If an aircraft experiences a 66 feet per second vertical gust while flying at VB, it would stall before exceeding the limit load factor. In turbulence, an aircraft would receive maximum protection from damage by flying at VB. But later, we will see that other factors must be considered when flying in turbulence. VB is quite a low airspeed, and it would take some time for an aircraft to slow from VC, the design cruise speed, to VB if it flew into turbulence. Therefore, at VC, the structure must be strong enough to withstand a 50 feet per second sharp-edged vertical gust, both upwards and downwards. Protection must also be provided for the remote possibility of a vertical gust during a speed upset towards VD, the design dive speed. Therefore, at VD, the structure must be strong enough to withstand a 25 feet per second sharp-edged vertical gust, both upwards and downwards. The intersections between the design gust values and their associated design speeds can be linked to form the complete gust load diagram. In practice, a slightly higher speed than VB will be used when flying in turbulence. This speed is VRA, the rough airspeed. VRA will give protection from both overstressing the structure and an inadvertent stall, and will be examined later. Please make a note of which design gust value is associated with each design speed. The examiners may ask you. We will now examine the effect of a vertical gust on the load factor, with this by now familiar vector diagram, the same one used to consider aerodynamic damping. The load factor, N or G, is calculated by dividing the lift by the weight. To illustrate the effect of a vertical gust on the load factor, we can use a sample written exam question. An aircraft is in level flight at a lift coefficient of 0.42. As the lift coefficient is the only data provided, and in level flight the load factor is 1g, the calculation becomes 0.42 divided by 0.42. A 1 degree change in angle of attack will increase the lift coefficient by 0.1. If the aircraft is subjected to a gust which increases the angle of attack by 3 degrees, what load factor will the aircraft experience? The gust will increase the lift coefficient by 3 multiplied by 0.1, giving a lift coefficient of 0.72. Dividing 0.72 by 0.42 gives 1.7. a new load factor of 1.7 g or an increase in load factor of 0.7 g. It is clear that for a given gust speed and aircraft true airspeed, the increment in load factor will depend upon the increase in lift coefficient per change in angle of attack from the gust. In other words, the slope or gradient of the lift curve. If the lift curve has a steep slope, as in the case of a wing with no sweep, or a wing with a high aspect ratio, the increase in load factor will be greater. A wing which is swept back, or a wing with a low aspect ratio, has a lower lift curve gradient, and so will give a smaller increase in load factor when meeting the same gust at a given true airspeed. Wing loading will have a noticeable effect on how much the load factor changes in a gust. Wing loading is the ratio between the weight of an aircraft and its wing area. For a given weight, the smaller the wing area, the higher the wing loading. The illustration shows a low wing loading. Because transport aircraft fly fast, it is common practice for the designers to provide as small a wing area as possible, which results in a high wing loading. For a given gust, the result will be a smaller increase in lift. A low wing loading will give a certain increase in load factor when the aircraft is subjected to a gust. Because of the smaller wing area on an aircraft with a high wing loading, the same gust will give a smaller increase in lift and a smaller increase in load factor. We have seen that a gust can increase the load factor and bend the wing, but it could stall the wing instead, in which case lift will decrease. There is thus a minimum speed at which it is safe to fly in turbulence to avoid a stall, and a maximum speed to fly in turbulence to avoid overstressing the structure. To provide a speed margin from both these eventualities when flying in turbulence, the rough airspeed, VRA, is used, which we will examine in detail next. We will now examine the rough airspeed, VRA. VRA is the operational speed at which to fly the aircraft when turbulence is encountered. The illustration shows pressure altitude increasing vertically and equivalent airspeed increasing horizontally. The first speed to consider is the 1g stall speed. The next speed to consider is the speed at which the wing will stall if subjected to a vertical gust of 66 feet per second, labelled alpha. The next speed is VMO, MMO. And the highest speed that concerns us is VD, MD, the design dive speed. Next is the speed at which the maximum structural strength is reached if the aircraft is subjected to a gust of 66 feet per second, labelled Bravo. The 1.3 g altitude is the maximum altitude at which the aircraft can sustain an increase of 0.3 g without buffet. If the aircraft experiences a 66 feet per second vertical gust at all speeds above line alpha, the aircraft will not stall, and at all speeds below line Bravo, the structure will not be overstressed. Therefore, the rough airspeed, VRA, should lie somewhere between these two speeds. VRA gives equal protection between accidentally stalling and accidentally overstressing the aircraft. So is the operational speed at which to fly the aircraft when turbulence is encountered. Line Bravo is a curious shape, because different parts of the structure become critical at different altitudes. This line is actually the lowest speed boundary of a collection of curves at the higher speed end of the chart. In the next lesson, we'll take a look at landing gear and flap limitation speeds.